Well, thanks for coming, everyone. It is my pleasure. I'm Dr. Robert Stalls, physics professor here. It is a real pleasure for me to introduce my student, Merlin Ginther. Merlin has been a student of mine for 3 or 4 years, and he has always been an outstanding student, a real self-motivated student. He devised this project on his own because it's something he wanted to investigate. I've pretty much been sitting back and watching his progress, giving him occasional hints, but the work is all his, and it's an amazing bit of work. So please join me in welcoming Merlin Ginther.
Okay. So last semester, I worked on the applicability of van der Waals potential to computational fluid dynamics, or basically how a specific model for molecule interactions can be used to model airflow and liquid flow. So today I'm going to talk about the statement of my problem, the formulation of the model itself, the justification of why the model works, and finally the results of the model. So my mission was to design an experiment to discover if the van der Waals potential could be used to model fluid dynamic behaviors of how air flows and liquids flow around obstacles and through obstructions. So some of the advantages of this is it's a molecular dynamics model, meaning you're only looking at individual particles as opposed to all these vector fields and such. It's a lot simpler than what's currently used, which is a Navier-Stokes equation, which uses partial differential equation, and it's like grad level work to work with. And it uses just the properties of the gas particles themselves to get the behavior instead of assuming anything about the fluids. So the reason that this is important is because almost all of the problems that we face in the real world involve fluid dynamics. From airplane flight to rockets, very few problems actually are in a vacuum. The fact that you can hear my voice right now is because there are pressure waves moving through the air from my mouth to your ears. So why study fluid dynamics? Well, if we have a good model for fluid dynamics, we can look at all these real problems and we can study how air flows around anything. Anything. Even a cow at Mach 8. So in actually formulating this model, I kind of went and stopped using the actual van der Waals model and used a very close approximation called the Lennard-Jones potential. This is good because I'm only looking at the overall behavior, and it's much easier on the computer to carry out this kind of model. Then the equation of motion needs to be derived for a single particle. With that done, we can then take that to many particles. We can then find numerical techniques to solve the equations of motion, the paths that each particle will take, and finally figure out how the program should handle obstructions and collisions with boundary conditions. So this is the Lennard-Jones potential. It depends on two constants, which are epsilon and sigma, which is basically the lowest point in the potential well, as well as the distance where the electric potential between the particles is 0. The overall equation itself depends on the parameter, the script r, which is just the distance between the two particles. So if I skip the calculus and the kind of nasty stuff, you get that the force on any particle is the sum of all of the forces from all of its neighbors. In this model, we say that all the particles have an identical mass, which, for if you were looking at a uniform gas like just nitrogen, that would be true. And basically, the way this is denoted is the force on a particle I from all of its neighbors, which are each particle is taken as a different j value. So these are the charts of both the force and the potential energy versus the separation distance. The potential energy is kind of like the gravitational potential energy. And so here you can see where those parameters, sigma and epsilon, actually come into play with the behavior. And you can see that at the bottom of the well there, where the potential is at epsilon, that's where you also get a force of 0. So this is kind of like the equilibrium point where the particle is just kind of happy to stay there. So talking about the principle of superposition, that statement is just here that the force from all of the neighbors, you add the magnitudes and the directions together to get the total force, which is all you're really interested in when you're looking at how a single particle moves. So in order to get a solution to how these particles move, we're using what is called an n-body problem, just meaning more than 2 objects moving around. And as such, you can't solve this by hand. You can't write an equation that tells you how it's going to move. You can't even do this for 3 bodies moving around, and this simulation uses about 16,000. So we proceed by numerical techniques, which means that we use algorithms to approximate very closely to where each particle will be, say, a millisecond later, and then use that to get the next step and so on. For this, I used an algorithm called a 4th-order Runge Kutta. And so what the 4th-order Runge Kutta will do, we also call it an RK4, is it will look at the conditions based on where it's at, its current position, velocity, and the acceleration from the particles around it. And it uses 4 different steps that you can see here to approximate a line from its current position to the real position sometime later. And here you can see the initial position at 1, which is yn, as a black dot. And then at yn plus 1, the black dot is the real value, whereas the white dot is our approximated value, which is, if you're using a small enough time step, will be very close to the real solution. So this is the code, kind of a flowchart of the code that I wrote. Here there's this particles method. It holds on to the particle's position and velocity for all the particles, and also records the data as it moves. It passes its parameters, the position and velocities, to this RK4 integrator, which uses the particle's position and velocity and acceleration to carry out that RK4 algorithm. And then to get the acceleration, it uses an acceleration differential equation, which will look at the particle's positions and tell you what the total acceleration is for every single particle in the simulation. Finally, what will happen is the RK4 integrator, RK4 integrator will pass the final and initial positions and velocities to this surface, which is a definition of the boundaries of the simulation. And that program will adjust the positions and the velocities to account for any collisions with boundaries that may have taken place during that step. So for the boundaries, some problems use an open boundary. This needed to be a closed boundary because of the small space that I was working with. And I used both quadrics and lines, which are described by this equation here. Because MATLAB is not good for doing algebraic solutions and manipulations, I used this equation because the solutions are then just given by the quadratic formula, which can just be coded directly in, and MATLAB can just spit out a number for us. So this is the basic surface that I used. It's a circle. It has a radius s. And this is how the collision correction is taking place. So you can see if a particle in one step would move from R0 to R1, this component that is perpendicular to the surface, to the boundary, is reflected, and the component that is parallel is kept the same. So the result, after you've done that, after you've reflected this component and left this component the same, is this reflected path in the bold here. So we have this model. We need to make sure that it works, that we're modeling real-life phenomena. So the simulation is tested through a series of what are called isothermal compressions, meaning that the container that the particles are in is shrunk continually, while the temperature and conditions inside the container are kept constant. After this is done, the data is fit to what's called a van der Waals equation of state, which is a model. It's kind of like an ideal gas law and relates the pressure to other parameters. So here's that equation of state, which shows that the pressure is dependent on the number of particles, the volume of the container, the gas constant, as well as A and B, which are constants that relate to every gas. Every gas has its own constants for A and B. So while collecting the data, the radius of the container is reduced in each simulation. So you have this circle that is continually reduced in radius, and the particles are placed in the same configuration in each run. The total velocity of each particle is also maintained the same, so that's how we keep that kind of constant temperature, if you will. while the direction of those velocities is kept random. That doesn't add any energy to the system, but it gives us enough chaos to model a real-life situation. Because we're only interested in how often these particles are colliding with the boundary, we allow it to kind of spread out and start interacting with these boundaries before we start collecting data. Otherwise, there's this kind of lag before the particles reach the barrier. So here, the orange dots represent my data from 3 experiments that are run, and this blue line represents the van der Waals equation of state for a compression. And what I did is I basically varied the parameters A, B, and the temperature to get this curve, to fit the data to my model. So the result of this fit is an R-squared value of 0.9953. One of the things that might bother somebody is I'm taking a 3-dimensional behavior, I'm generalizing it to 2 dimensions. So the way that I handled the volume is as if I was looking at a very thin disk that was 1 molecule thick. So what this means is that the particles can actually move in 2 dimensions, but not in 3. So using this volume allows us to use a 2-dimensional experiment and recover that 3-dimensional phenomena. I give some units here that are the kind of standard units used, but really I could say that the value of 1 in the simulation is 1 angstrom, which is a bond radius for an atom, or I could say that it's a kilometer, and these are like these massive particles. It doesn't really matter. What we're really looking at is the behavior. So the R-squared value of 0.9953 basically tells us that 99.5% of the data points that came from the simulation can be explained by that van der Waals equation of state. So finally, the results of this were to get a simulation of a wind tunnel and see if we actually get fluid dynamic behaviors that we can compare to real-life phenomena. So for this simulation, the particles are injected in one side of a wind tunnel, and they have a velocity going down the tube, and as they come out the other side, they're deleted in order to save memory space. So this is the result of the experiment. So what you're seeing here are what are called flow lines. So this tells you at any point how the air is flowing through this tube. And this blue circle is the obstacle in the tube, right? And what we have here is we call Stokes flow. You'll see this is basically the particles split around the container and then come back together on the other side. One of the things that you might notice here is there's kind of a gap here. And part of this is because of the scale that we're working with. This sphere had to be fairly close to the size of the particles because my simulation could handle about 16,000 particles. There's probably over a heptillion particles in this room, though. So in all reality, the number of particles that I could simulate is very small compared to the number of particles you see in a real-life situation. The other thing that is nice, though, is if we look at a density diagram, this is my simulation here, and this is a chart of the density in different regions, where a yellow value shows a high density, and the dark blue is the lowest density. And here is the results of another simulation using the Navier-Stokes formulation. So basically what you can see is that this model that is highly accepted in fluid dynamics matches this same geometry and these same pressure curves that you see in the Navier-Stokes equation. So the strengths of this model, it has good geometric correlations to the real-life phenomena that we see. It's a relatively simple model. It's just the molecular interactions, where if you start looking at the Navier-Stokes equation, you're looking at these really nasty partial differential equations. And the nice thing about this is instead of making any assumptions, we just start with the particles themselves and generate the large-scale behavior from the particles. The drawbacks of the model, it's computationally very expensive. So one simulation may take over 15 billion calculations, so that's a low estimate. And as I said before, only a relatively small number of particles can be simulated compared to a real situation. Without a friction term, so one of the assumptions that was made was there was no friction between the gas itself and these boundaries, because I didn't want to basically artificially bring in this behavior. So I tried to stick to behaviors that were realistic. As a result, that behavior did not come into this simulation, though. So in closing, the van der Waals potential is a good place to start with modeling fluid dynamics. By looking at the molecules, we can understand why we see the behaviors that we do, and we can begin to understand fluid dynamics better through these kinds of simulations. However, if we were trying to, say, simulate something like how an aircraft will function or how a cooling system will work, this technique is a little bit weak to find those kinds of simulations for testing products and stuff, because it is very computationally expensive. So that's all I have. Do you guys have any questions?